Okay, let's to start. First of all, with Manuel, we want to thanks to all of partner of the CVS Commission for the work of the year and for the invitation to this presentation. The idea of this presentation is to present a case study that today with Manuel, we are the host of this presentation, but we want to stress or have light that there are a lot of institutions of our country and the other country, and a lot of human resources that in the last 5 years worked together with us to achieve to this partially result that we're going to show you. With Manuel, we want to start with some motivation topics to put in context you. The first of them is how to volcanism affect the sedimentary routing system. To do that, we want to start with the first scheme of sediment routing system that puts the idea of a source to sink approach. And this model aims at deciphering the fate of sediment and processes that determine the journey of from the zone production to the zone of deposition of sediment. It focuses principally in sediment supply and the treaty nature of the sedimentary system. And one of the important things is that when we look this scheme or model, the sediment supply is mainly controlled by the climate and uplifting relationship in the source area. If we compare this model with the model presented with Manville and after Kataoka Kyoko, we can observe that the erosion appears in the two models. But in this model, the erosion has two meanings. One of them is related with the erosion of volcanic edifices, and the other is a relation with the eruption that produce the volcaniclastic material. So the first state that we want to stress is that if erosion is weathering and transport, we will be able to discriminate between them accurately in a source to sink approach. Let's imagine an imaginary situation of a transport system like that. We have a sample of sedimentary material that look like that. The question is, would you think that these particles were originated by weathering? Look at that particle originated or sample at 4,000 kilometers from the source, composed of more than 90% of pyroclastic strata. Look the shards, the shape of the shards, and the particles. Would you think that these particles were originated by epiclastic or sedimentary fragmentation in weathering? Would you think that this particle had a lot of transport? The response or the answer is absolutely not. This is maybe if I put a photo like that, you're going to think in primary deposit or sedimentary deposit. But the thing is that this imaginary transport system was not an imaginary, it's the case study. This is the location of the case study that is from the edge of the Andes to the Atlantic Ocean. In this system, in this large system, with this textural feature, we quantify volume of pyroclastic material that is around 2,000 cubic kilometers that were delivered to the sedimentary system. If I ask to any volcanologist, what do you think about this quantity of material? Is it's possible that think in this type of classification scheme of volcanic eruption. This is not the E, but the volume of pyroclastic material delivered to a system is a lot. But another topic and the last topic of the motivation is that who is the volcaniclastic supply regarding to eruption and buffering in the catchment area, because it's important to see how this volume was delivered to the sedimentary system. And to put in context, there are a lot of models in the last decade that focus in this topic. One of them is the model of Smith. This model go from and interrupted sequences in hundreds of years. And when we try to use this model for the textual feature that I showed, the synerupted sequences are huge and thick and have no sense in geological interpretation. So we look over. This is related with the Pinatubo eruption, and in this model we can see that the impact of the volcanic eruption and volume has two phases, and in the second phase there are instability of fluvial system that can last for thousands of years, but we have a signals in the transfer system that is more or long. So in the last year, there are different works that in the different arcs that analyze the long-term complex volcanostratigraphy of volcanic arcs. And I want to highlight the work of Pitcher because these authors work in the same formation that this model was devised. So in this case, Pitcher find an overlapping of different volcanic eruptions that are imprinted in the model of Smith. With this motivation issues, the aim of this presentation is to define a synerogenic volcaniclastic sediment transfer system from the Andes to the Atlantic Ocean for the Miocene using high-resolution temporal and spatial schemes to analyze the interdependence of boundary conditions that imprint environmental signals in the geological record, and to develop high-resolution time processes scheme for a stage of the Andes, accounting for the cyclic and fractal signals in the volcano sedimentary rim. To start, Manuel, in the second part of this presentation, I'm going to show you how we build the different phases model. In this part of the presentation, we want to show you the landscape and different photos of the deposit. In the south zone, we record mainly primary and resedimented pyroclastic deposits like that. In the bright volcaniclastic resedimented deposits and different type of labile or ash out deposits. From the source to transfer zones in the system, we record alluvial to lacustrine section. Look at that, totally stressed by pyroclastic material. And in the last part of the transfer system, from the transfer zone to the sea, we record a base load and mixed load fluvial system. This is a floodplain succession that interbedded with a fluvial channel body, or bodies, in this case is one, but look at that the quantity of pyroclastic material along the whole system is huge. It's between 80 to 95% of volume. The result of the different approaches that we carried out in the last year shows a conceptual scheme like that. We have a premier Miocene basin rock. We have a partially integrated sedimentary system stressed by pyroclastic material that go from the foot of the Andes to the sea, originated different sedimentary environment like volcaniclastic apron, lacustrine system, or fluvial system. The second part of this presentation is related how the interdependence of boundary conditions imprints the environmental segments. And to address this topic, we want to present the concept of environmental signals that are changes in sedimentary production, transport, or deposition that originate from perturbation of environmental environments such those. The important thing is that in this definition, the volcanism, in the definition of Romans, were not included. So, do you think that volcanism cannot include in a concept of environmental signals when we address models, source to sink models next to volcanic arcs? It's impossible to address. So we are developing this part of environmental signal. And to analyze environmental signal, we have to consider two variables, mainly two variables. First of all, the time, and the other is the forcing factors or forcing variable. We would just stress that if we present all variables like climate, tectonic, and sea level changes to the Andes, maybe or maybe not, will be a presentation itself. So we're going to focus in the variables that affect the volcanism into this system. And to do that, we're going to focus in the magmatism in the edge of the Andes. This is the picture of the study area. This is the Atlantic Ocean, and this is the edge of the Andes. And at the edge of the Andes, we record several magmatic or plutonic stock. That this plutonic stock have the typical signature of arc volcanic or magmatic series. And when we analyze the age of this plutonic stock after the Cretaceous times, during the lower to middle Miocene, we record an unusual magmatic activity of the Patagonian batholith. So, with this idea that we fix one of the forcing control, we want to stress that we have time to analyze the signal into the system. With this objective, we located different key stations along the system, and carry out different geochronology and magnetostratigraphic scheme that show this type of arrangement of this transference system, this Miocene transference system stressed by pyroclastic materials. If we look at that picture, we can see that the transference system is so complex in time. The pattern of the transference system, the record of the transference system is so complex. First of all, when we correlate this scheme with the server analysis, we detect that there are two main sequences. It's important to highlight that it's time, it's not volume. Manuel, after that, going to talk about these special sequences, sorry. The other thing is that we didn't present the other forcing factors, but this is the curve of the relative level change of sea level. We can see that in some cases the hiatus in the distal zones are related with the sea level variation, but in the other, we record that when we compare with the tectonic activity, the hiatus in the proximal area are related with the accommodation space, the negative or positive accommodation space related to tectonic uplifting climate balance. So the first learning that we can stress is that we can't analyze a volcaniclastic source-to-sink approach without estimate the other forcing factor, because going to determine the feature of the characteristic of the system. To analyze in deep the volcanic over time, the environmental signals, we devised this methodology approach that combine the common methodology approach of the physical volcanology or sedimentology. We add two different methods. One of them is the ECPMS analysis, and the other is an electron probe microanalysis. We're going to show the result, the partial results of these methods that we are doing. It's important to highlight that to discriminate the signals of the Miocene volcaniclastic temperate system or the impact of the eruption, Miocene eruption, we handpicked different volcanic circons and analyzed the volcanic circons younger 60 million years. Single grain analysis of crystal circons. To the analysis of electron probe microanalysis, we select different samples and analyze single pristine 210 metric shards, following the protocols of Pierce. So let's go to see the first or partially results related with the ECPMS. And to do that, first of all, we going to put another imaginary situation to may analyze this kind of scheme. So if we have an initial or onset of eruptive period of epoch, we're going to record a point because the single grain going to be the same of the positional age. Imagine that if we record a total period or epoch, in this case is an epoch, from the onset to the ending, and we only record the primary product of the eruption, the system or in the scheme, there were a straight line that going to record all the ages where the single grain going to be the same over the positional age. But if we have reworking of other rocks of the system, we're going to we're going to have the same depositional age, but we're going to record other signals related with the recycle of the volcanic rock of the origin. So the result of these methods is the following. In your left, this is a typical section that we carry out to establish the chronostratigraphy and magnetostratigraphy control, the sedimentary section. In this case, we record 42 pilosoids, and in the right hand of this section, we have all of samples that we record samples to the different methods. If we analyze the scheme, it's important to highlight that the samples into the scheme is not located by place into the system. It's only located by the age. So it's important to highlight that samples of the different part of the system have the different signal. And if we analyze, we record that there are divides or spaces for the positional hiatus. We have a tendency of samples with low dispersion, and to the end in each of these cycle, to the end of the cycle, we record an increase of reworking of the material. When we correlate that sample with our sample with the samples or the phases analysis result, this corresponds to primary eruption fed and resedimental-like deposits. Resedimental-like deposit, because this is also resedimented, in some cases, resedimented like deposit to rework volcaniclastic deposits. So the second rendering that we want to stress is that in this part there are a diffuse way to discriminate in this system what kind of materials, secondary material, are resedimented or reworked with the idea of cut and write analysis. For instance, with the shape of shards, of estimating the fragmentation of shards, as we as I showed in the motivation case. The thing is that when we try to test with other method one of this cycle, we record the same. This is the sample that we did for electron probe microanalysis of different shards, and we record that from the onset to the ending of the cycle, we record that there are signals that started to show different type of signal along the time. For example, see the distribution for this point to this point with dotted line are the previous data. So this implies that we have a signal, but after that, inside the system, there are other events that imprint or overlap over the first, and in a continuum time-space scheme, imprint the volcaniclastic signal along the system. The third learning that we can stress to this is that we record a volcano sequence of third order that one the scheme of time that include two sequences. One of them is that, and the other are these sequences that at this scale we can divide in two volcanic sequence of the second order. What's meaning that in terms of analysis to analyze the volcanic signals into the system, that we record 3 cycles. The cycles started and to the end previous to the depositional hiatus started to record the material. This means that long part of each of this cycle disable the weathering of the erosion aging of the common sediment routing system. It's a hypothesis because this is a preliminary result. We think that there are large inverted drones, the catchment area, like in this scheme. This is a thickness of sedimentary part that's compared with the thickness of the fallout deposit. We are in this situation for most of the cases. In this signal, we receive signal of minor volcanic eruption that continue deliver the same signal into the system. Why we have this hypothesis? For that ask the answer going to do Manuel, because he going to do a focus in this particular cycle that, as you can see in this first impression, there are overlap between the primary and reworked deposit, and the time that expand this cycle was so short. And remember that when I showed the stratigraphic scheme, I said this is time, it is not volume. So in this case, this is time, but it's not volume too. And Manuel going to show you what happened in this case. This is the first part of the presentation. Manuel?
Yes, I'm here. Okay, now we are going to develop the third aim of the talk, which is about the high resolution time process scheme for stage of the Andes, for the stage that Leandro mentioned before. So for that, we are going to focus on the proximal zone of the sediment routing system. We are going to focus here because this region is important because we have the interaction between magmatic arc and Earth surface processes. Since we have the preservation of contemporaneous intrusive rocks, Miocene intrusive rocks, and several retroarch deposit centers with volcaniclastic deposits. So if we think about magmatic arc and volcano-magmatic arc processes, it is well known that they are wide span in time scale. So we have from eruption epochs or periods from millions of years towards eruption units or even phases or pulses in lapses of minutes or seconds. So if we try to see a timescale approach in sedimentary epiclastic system, there has been several advances in the development of architectural units. And different units, these architectural units can record from small-scale bed loads processes to complete sedimentary systems. So each architectural unit in sedimentary systems are boundary but unconformities with different timescales and processes. So if we try to mix these two approaches, we are going to try doing that to analyze volcaniclastic processes as a continuum through the time. So for that, we perform several logs through south to north and west to east transects. Through the logs, we notice several volcanic and sedimentary phases, and we group the phases in phases associations and architectural elements. Those elements are bounded by unconformities, which has a distinctive volcanic or an environmental significance. And also the elements were grouped into volcaniclastic sequences. By combining phases analysis with the unconformity bounded stratigraphic units and contrasting with historical events and ancient records, we are going to develop or try to develop this hierarchical scheme. There are some logs from north to south and west-east. In those logs, we identified 13 phases. There are primary phases, primary volcaniclastic phases. Just to mention some of them, and you can look at the picture, there are lapillitaf deposits, which are massive or also diffuse stratified, evidencing PDC deposits with different fluidscape to intermediate to tractional dominated lower flow boundaries. And also we have centimeter scale lapilli and tufaceous deposits, which were interpreted as fallout deposits. If we see the secondary volcaniclastic phases, there are all the phases are very ash-rich in composition, and are characteristics the ash-rich massive sandstones with subtle paleosoil development, also contain some fragment of fossils. And these sandstones can contain different lithics from pyroclastic deposits, just fragments of PVC or pumices. But there are also other more epiclastic in composition phases, like the lower ones, which are characterized by massive. Oh. We are here, yeah. Sorry, something happened. Okay, sorry. So we have massive conglomerates with epiclastic lithics and also channelized deposits evidencing turbulent, unidirectional turbulent stream flows. And the other phases, more massive and poorly select, were interpreted as sediment gravity flows deposits. So the phases, as I mentioned, were grouped into phases association, and we have 8 architectural elements. The first architectural element is characterized by a PDC deposit in proximal sites with a valid point geometry. These deposits are correlated physically. You can continue it in the field to more distal deposits, PTC deposits, in which we have a lobe-like PTC shape. Sorry. So below these facies associations, there are veneer PTC deposits characterized by more tractive dominated deposit, yes, which laterally toward internal basement heights, this association is transformed into massive deposits, evidencing probably a lateral flow transformation of tractive dominated PTCs. Other deposits, primary deposits, are related to sheet-forming follow deposits, which were related to the tufaceous and lapilli facies. And when we see the secondary facies associations and architectural elements, we can see tabular massive lapilli, tabular asheric sandstones, which are buried one over the other, and laterally and vertically they are related to shallow water bodies with siltstones, with diatomites. The last facies association is related to the epiclastic rich deposits with some channels and semi-gravity flows. These secondary deposits were interpreted as proximal to distal volcaniclastic alluvial systems with shallow water bodies in more distal sections. So now I'm going to group again this facies association in volcano sequence as Leandro mentioned. We define two volcaniclastic sequences of third order. The first sequence evidences the position of a volcaniclastic alluvial system with an irrational stacking pattern dominated by high sedimentation rates and pyroclastic resedimentation. This sequence evidences a high-frequency alternation between pyroclastic deposits or explosive eruptive events with resedimented events. So this sequence evidences the drowning of the North Patagonian retroarch sediment arteries and intermontane deposits. The second volcaniclastic sequence indicates the propagation the progradation of the volcaniclastic alluvial system, and it's dominated by substrate reworking over erosional disconformities. So it may evidence the environmental readjustment of local base levels and drainage networks. Which is interesting here is to see that eruptive records, primary deposits, are with diverse explosivity and frequency are recorded in both sequences. So if we see the first sequence, volcaniclastic sequence 1, we have the record of the PTC deposits in two outflow units. Facies association 1 and 2 were correlated laterally, forming PTC deposit with minor thickness or minor changes in thickness and distal temperature conservation. So we interpret a high mass discharge force current regime. Otherwise, the facies association 3 compound another outflow unit below the other one, which is which can be related to an inertial current condition because of the tractive dominated facies and the high thickness changes through internal heights. So in this volcaniclastic sequence 1, this may evidence a less frequent and high explosivity index volcanic eruption with the first column collapse phase, which followed with a caldera collapse phase. If we see the lapilli phases from deposit from fallout, they are distributed in the two sequences, the volcaniclastic sequence 1 and 2. So this alternation of fallout deposits evidence more frequent and probably less explosive events occurring during the deposition of both sequences. So to make an integration of the conceptual timescale and develop the hierarchical timescale processes, just to remember, we are within a second order. Sequence in which we record third order sequences. The first one, volcaniclastic sequence 1, it evidences the rebooted of post-eruptive processes, and we have like the climax of eruption rates with the high Bay record. And the upper, volcaniclastic sequence 2 can be related to inter-eruptive-like processes as a delayed response to the environment from the environment to the first high eruption rate of the volcaniclastic sequence 1. And overprinted to both sequences, we have several eruptive events with minor explosive indexes. So when we see within these volcaniclastic sequences, we can notice different order of processes. As Leandro said, we have this picture of Grant in which he showed a first phase of post-eruptive resedimentation, which is predominant in volcaniclastic sequence 1 with poorly developed paleosoils. And the continuous fluvial instability or alluvial instability, environmental instability, can be continued for thousands to tens of thousands of years, which is evidenced by the epiclastic incorporation of the volcaniclastic sequence 2. And this also noticed a bed load evolution of the systems. But within these volcanic cuisines, it's important because there are some hidden processes which can help us to understand the timescale of the deposits and the interactions. For instance, in this paper, the authors describe several paleosoils from Mexico next to volcanic areas, and they noticed that paleosoils can be developed from hundreds of years, like this example, up to almost a million of years. So in the terms of hundreds of thousands of years. So this means that paleosoil development can be overprinted and expanded between post-eruptive to inter-eruptive periods. Something similar occurs with diatomate and substrate colonization after eruptions, in which in this crater the author described like bars with diatomite proliferation, in which the timescale of these processes are within the year or even the season. So when we have active volcanism and primary deposit, there are sort of processes which are between the year and the seconds that are, I'm not going to get into this, but I just show a nice picture of Rainer Kukla in which we can see how lower flow boundary zones can change and migrate, and phases can be correlated in lateral and vertical, can change from one to another. And also there are some processes which imply remobilization within eruptions. I mean, during the eruption, there can be processes of remobilization. So those processes I mentioned before about can be related to lateral flow transformation or even the reprocessing of the deposits during the eruption again. So just to conclude this presentation, the Miocene volcaniclastic sediment transfer system from the Andes to the Atlantic Ocean operate over the long term, controlled by a volcanic engine. As Leandro showed, the system evolved into first-order sequences that show control-related stratigraphic environmental signals propagating differently from source to scene. According to the controls, as you see the sea level changes or tectonics and magmatic controls towards the Andes, you can generate and preserve different signals in stratigraphy. So single grain silicons analysis and yards suggest that the volcanic engine was characterized by episodic volcanism that stressed the catchment areas from hundreds of thousands of years to millions of years, disabling the erosional engine of common sediment routing systems. The positional hiatus indicates that complex interdependence relationship exists between tectonic and magmatic plumbing system, which triggered the large volcanic eruption. And finally, the source region is influenced by time-related magmatic arc and Earth surface processes. And this is a table that we are developing in which we are trying to explain the different timescales without unconformities and related to arc signals and environmental responses. But the important thing here is to mention that cyclic long-term high to low magmatic arc eruptive conditions determine fractal and overprinted mid to short-term environmental responses, which can also be instantaneous to hundreds or thousands of years delayed. And that's all. Thank you.
Thanks a lot, Leandro and Manuela. The presentation was very good and very clear. And also I think it's a really interesting topic overall because, we can see the control of volcanism and sedimentation under an ancient perspective. So something that we can see in the modern environment, transferring into ancient environment. Really, really interesting. If someone have any question, can take down the question in the air or just in the chat. Don't worry, you can write down. While we are waiting, if someone has a comment, I would like to ask you something really quick. If you had some comparison between the production of sediment by volcanism from the production of sediment by, let's say, tectonic erosion in the same context, I mean. So are you planning to do this or did you do something like this? So just to compare which is the difference, the difference capability to response of the environment between tectonics and volcanism.
I can.
Leandro is mute.
Yes, Andrea. The problem that we have with this topic is that first of all we have to determine what is the signal of volcanism. For example, the sediment routing system is a model that in the last decade is quoted a lot. But when you see the different systems when the model was set are few. So we are in the Andes that we had to modify the definition of environmental signal and establish. We are working in a sediment routing system that has volcanism. So the idea in this first situation is, in this part, or in this first part of the case, is determine the impact of volcanism over the sediment routing system. Let me show you what one of that you can see my screen.
Yes.
Yes. We analyze this cycle, this volcano sequence of the order, but this is not a volcano sequence. This sequence has few volcaniclastic and volcanic primary products in comparison with that, and is dominated. This sequence is dominated by between 80 and 90% of pyroclastic material. In this case, the 80% of material is epiclastic. So we are working in this sequence too, and the problem in this sequence, like the Andes produce in the normal state of the arc, produce basalt volcanism in the retro arc.
Okay.
We have another complex situation that the epiclastic material is related with production of volcanic gas, but we erode it from basalt unit. So we have an uncommon sediment routing system. So I think that it's a step by step. We are starting to work with YPF to record these sequences in the seismic of the shelf, and step by step we are thinking in that, but I think that it's matter of year to start to achieve this topic.
Okay, thank you. Let's see if someone has a question. No. Okay, if we don't have any question from the audience, I think we can close this webinar. This is the last webinar of 2025. I have to acknowledge again Manuel and Leandro. Thank you again for participating, for accepting the invitation. Oh, someone is writing, maybe. The presentation was really interesting and really focused on our topic of the commission. For all of you, please follow us on our social media, on our website, and you can watch this webinar, also all the other webinars, because it will be uploaded on our YouTube channel. So you can, if you're interested, if you want to see again what Manuel and Leandro show us, or what has been shown by all the other speakers during those 2 years of webinars, please visit our YouTube channel. Follow us on LinkedIn, on X, on Blue Sky, on all the social media that you can also in Instagram and Facebook. And happy Christmas and Happy New Year, everybody. See you next year for our new webinars of 2026 by the Commission of the Volcanogenic Sedimentation. Bye-bye.
Bye. Thank you.
Bye-bye.